Hey, what's up, guys? Yeah, so in this video, I want to introduce another interesting idea called quantum Forrelation. Okay, and this is, I think this is produced by Aronson. Sorry, Aronson. I think 2014 and also 2009. Okay, you can check out the paper. Basically, this is like famous quantity that and there is a problem called quantum Forrelation, which produce the oracle separation between the BQP and the pH. Also, in this video, just give you the very simple idea that how this Forrelation comes from in the very simple quantum algorithm. Okay, so the idea is very simple. Idea is that given f and g, okay, from 0, 1 to the n to -1 and 1. So basically, it's a phase. Sorry, it's not phase, just given any bit string with length n, then I just give -1 or +1. Okay, and then one can define a Fourier fg. Basically, it's the coefficient. You can imagine that basically this is somehow like the inner product between the Fourier component. So it's like defined to be 1/2 to the n. Okay, so let me just define it. Capital N to be 2 to the n. Okay. Okay, so the definition is following. So the definition is this. Okay, so it's 3n divided by 2, and the summation of x and y, both from 0, 1 to n. So you consider every input, and then you consider f of x, xi of y, and then -1 xy. Okay. So this is the definition. So this is called the Fourier of f and g. Also, be given two Boolean function, which is from -1 to either plus or -1, and then you just compute this sum. Okay. So idea is that if you know some characteristic theory or group representation, then you can imagine that this guy is basically if you just sum over like y, then this guy you can imagine that this is the like Fourier analysis in f2 to the n. Okay, and you just inner product with this f of x. Okay, so this is called Fourier. And one can define the k-fold one. Okay, so actually there's a k-fold. So this is this guy is twofold because there are two functions, and then you can define k-fold. K-fold is that you have f1, f2 up to fk, and then there are both some function from 0, 1 to the n to -1 and 1, and then you can define f of f1 up to fk. Basically, it's the same thing. 1 divided by 2 to the k plus 1 to the n divided by 2. Summation of xi, so every I is from 0, 1 to n, so I from 1 to 2 up to k. And then it's f1 x1 -1 x1 x2, and f2 x2, and then -1 x2 x3, and then f3 x3, and up to finally should be -1 to xn -1 dot xn as previous one, and fn xn. Sorry, xk. Okay, k. Okay, so obviously that if you put k equals to 2, then you will get the twofold Fourier. Okay. Okay, so the interesting thing is that this Fourier has a very simple quantum algorithm. Okay, so I will just do twofold case. So I will just produce a twofold case. Simply speaking, there is a very efficient quantum algorithm on this Fourier. Okay, so basically if you start with BQP and then you have two oracle, one is f and g, then you can just construct this Fourier very simple. Okay, or you can just measure this very simple. Okay, so the model one. Okay, so model one is this. You start with the 0, 1 to the n, where it's all product state, and then you go the hard mod, right? So you create all the superposition, and then you do f, and then you do hard mod, and you do g, and then you do hard mod, and you measure. Okay, So this is the simplest. This is the first model. I think it's this is a simple model that one can think of. Okay, so let's do it step by step. So in this step, then you will get 1 over square root of 2 to the n summation x. So let me just omit the so when I write summation, I write summation x, then I'm just write x sum over x from the dense and bit string. So just for the convenience. So x, okay, for this one that I get x and f of x, right? This is, remember this is Curie model. So each of f of x is plus or minus 1, right? So the norm is still 1, okay? So you get this. Now you hard mark again, right? So you get 1 over 2 to the n summation x and f of x, and then you do y, right? Because x change into y, so minus 1 xy y. Now you get g. So for this part, you get 1 over 2 to the n 3n divided by 2 f of, sorry, there's no 3n divided by 2. It's still n divided, it's still n. Now this y becomes g of y. So you get f of x minus 1 xy g of y, y. Okay, so now xy. Now the final step, there is still hard math, right? So you need to change this y to z. So we have y to 1 over 2 divided by n 3 divided by 2 summation of x, y, and z. And the f of x minus 1 xy g of y. So now this need to be minus 1 yz to the z. Okay, so you just measure O0. So this guy, let me just say measure O0. 0, 0, 0. So it's measure 0 to n. Okay, so the probability that the measure 0 to n will be put z equals 0, right? So put z equals 0, then you don't have this term, and then it's xy f of x minus 1 xy g of y 1 divided by 2 to the 3 and divided by 2. Exactly, is this the amplitude of this, right? Okay, so this is just the Forrelation. Okay, so if I promise you that either Forrelation is very large, then you can get large. You can have probability to get 0. And if your Forrelation is 0, then there's no way that you can get 0. Okay, so that means that if Forrelation is large, then I can just run this simple model and I test 0 to the n. And if I get 0 to the n, then I have the high confidence, or I do lots of time. I have the high confidence that f this phi is large. Otherwise, that phi is small. Okay, so this is the first model, and okay, and this first model can be generalized. So let me just do the generalization. So I will not give the proof, but you can easily see a proof. So if you can start from 0, 1 to 0, 0 to the n, and then go hard math to the n, and f1 h to the n, and you get f2 h to the n. Keep going until the ufk h to the n, and you measure. Okay, and you can prove that these measurement results will give you the phi of f1 of the fk squared. A probability that you get 0 to the n. Okay, so this is still the model 1, the model that you can get the quantum Forrelation. Okay, so instead of this model 1, what is this? The problem for this model 1 is that actually you Curie twice, right? Because I have f and I have g, so I need to Curie twice, right? But there's a model 2, which only takes k divided by 2 Curies. Okay, sorry, should be cell. Okay, cell function. Okay, so the previous one, if k is 2, that we take 2, right? But there's a model quantum model that only takes one queries. Okay, so you might think, oh, how is this possible, right? But it's amazing there's someone come up with this. Okay, right? So I can initialize 0 and tensor with the plus. So plus is just 0 plus 1. Okay, then I conditionally on, let me just say, the algorithms, I conditionally on 1 and 0 and do different behavior. Okay, so if the 0, if the this bit is 0, then what I do is the following. So I do the following step. I start from h to the n, and I do the f1 query. Let me just use fg. Let me just use uf1. It's fine. And I do hn, and I do the uf2, and I get u of fk divided by 2, and then take the cell, take the cell, and do the h to the n. Okay, and if it's 1, so this is a 0 path. If I conditionally I get 0, I do this path. If I get 1, I get another path. Okay, so what I did is that I start with h to the n, and do the ufk, and h to the n, and ufk minus 1. Keep going until I get u of f cell k divided by 2. Okay, plus 1. Okay, and after that you will get some state, right? You'll get some complicated state. Okay, and the complete state, right? Let's say this state is psi 1, and then this state is psi 2. Okay, so after that you will get psi 1 0, right, plus psi 2 minus 1. Okay, so now you measure the second qubit in plus or minus 1 basis. Okay, so this means that you can write as square root of 2 psi 1 plus psi 2 plus, and 1 over square root of 2 psi 1 minus psi 2 minus, and then you measure in the second qubit and in the plus or minus basis, and the result is amazing. Result is that the probability that you get plus is half 1 plus phi of f1 up to fk, and non-trivial. Okay, very non-trivial to prove, but this is the result. Okay. Yeah, so let me just this proof is just cumbersome, right? But I can do like 2. I can do like k equals to 2. Okay, so let me just provide the detail for k equals to 2. K equals to 2, we only have f and g. Okay, so let's write f and g. So my starting state is this, right? So after the pass, right, I get the for 0 to the n, then I get Hadamard and f and Hadamard. Okay, so for this one, the first step, let me just write down, I get Hadamard and f and Hadamard. Okay, so my state will be this will be 1 over 2 to the square root n summation x. For this one, that I will get 1 over square root 2 to n in the x f of x, and I will get something as I just previous says, 1 over 2 to the n summation y minus 1 x y. So we just write x y and the f of x y. Okay, so this is my first part. Okay, so how about my second part? So my second part will get h to the n and the g. That's it. Okay, so second part is h to the n and the g. Okay, so obviously this is 1 over square root of n summation of x g of x. Oh, by the way, I think I made a mistake on this, right? Because there's a still x here. Okay, so yeah, this is our state. So our state is this. This is psi 1, right? This is psi 2. So our state will be psi 1 plus 0 square root of 2, 1 over square root of 2, psi 2, 1. Okay. And I need to ask the plus or minus, right? So I need to change it. So as I said, right, you can basically, I will start from here, right? So this plus, right, is basically 1 over square root of 2 plus and then minus. So total you get half of psi 1 plus psi 2 and then plus. Okay, and then there's a minus part, so you have of psi 1 minus psi 2. Okay, so what? Okay, so the probability that you measure plus will be just proportional to this guy amplitudes, minus will proportional to these guys amplitudes. Okay, so all I need to do is just compute the inner product of these. Okay, and the computation is cumbersome, but that's hopefully we will not. Hopefully we will like survive on this proof. Okay. And okay, so let's do this. Right. So as I said, right. So let's forget about this half. I forget about this half, right? Because I will calculate the inner product of this. I will calculate the inner product of this, and I know that it's proportional, right? So I will like do the normalization after that I finish the calculation. So let's forget about this half. And okay, so I can see I can summarize two of these, right? So let me just do some simple step. Right, since that this is x, right? This is y. So hopefully I can change this into x. And exchange xy, this is still alive. This is still the same. And f of x need to be f of y. Okay, and I forget about this. I make somewhere y to here. Okay. So what is my state? Right. So my psi 1 and psi 2. Well, basically just this. 1 over 2 to the n summation of gx x plus 1 over 2 to the n summation of x and y and minus 1 x y f of y. And let me just write this. Let me just pull out this sum of x. Okay, I suggest that you do this calculation. Okay. Okay, here, right? Sorry, it's incorrect. It's 1 over is this. This kind of calculation is like cumbersome. Although yes. Okay. 1 over square root 2 to the n g of x, 1 over 2 to the n summation of minus 1 xy f of yx. Okay. So I want to calculate the absolute value of this, right? So since it's the same as I calculate the norm, so I want to calculate. So I want to calculate the following. Right? And I need to calculate amplitudes, right? So the norm of this guy is the same as sum over each x, the amplitude of each x, right? So I need to sum over x. Okay, so this is what I need to compute. Okay, and so okay, so let me just compute. So the first sum x, and yeah, okay, so it's 1 over 2 to the n g of x squared. Okay, so notice that these f and g are plus minus, so square is 1. Okay, so square is 1. What? Okay, plus summation x. So now I can do so it's absolute value squared, but all these are real numbers, so I can just take the square. Okay. So I get 1/2 to the n divided by 3n divided by 2. And the summation of y minus 1 x y f of y. And the g of x. Okay, so you can see that, oh, this guy is the Forrelation, right? Obviously. Plus the final term, right? So final term is 2 to the 1/2 to the 2n. And the summation of x. Notice that this is this guy squared. So it's y minus x y f of y squared. Okay, so this guy is a cumbersome that we will like deal with this bad guy. Okay, so this term is what? 1/2 to the n, sum of 1, right? So x is, there's a 2 to the n, so it's 1. And this guy, right? Oh, sorry about this. So when I times this, there should be another 2, right? Because, yeah, right, this is 2 here. So this is 1/2 5 fh. And there's a guy here that this guy. Okay, so let me just make another page. Hopefully we deal with this guy. Okay, so it's y minus 1 xy f of y squared. Okay, so the quick calculation is do this 1/2 to the n. I don't know whether you guys have intuition or not, but usually when you calculate this guy, this kind of f2 for the transformation, the only thing you need to do is just move this x into just exchange the sum and use some identity. Okay, so now you can get y and z and x minus xy f of y minus xz f of z. Okay, so so there's 3 of them. And the things like sum over x. So this guy is just minus 1 x y plus z f of y f of z sum over x. Okay, so notice that this is this, right? So this minus 1 to x y plus z is 0 unless y equals to z, right? As a vector is y equals z. Okay, so this is 1/2 to the n, summation y and the z and the x and the y z. Sorry, x disappear. Right, x disappear, right? Because and the f of y and the f of z. Okay. Right, so yes, so minus 1, right? So you get this. Sorry, I still forget about this 2 to the n. Right? Because if y and z are the same, then this will be 1, 1, 1, 1, 2 to the n. So there's a 2 to the n here. Okay, so since y and z are the same, so I can just kill z and change z to y. Okay, so I get 1/2 to the n, 2 to the n, and the summation y f of y squared. And then remember that the f is 0 from 0, 1 to the n to plus or minus 1. So this guy is still 1. And then so its summation y is 2 to the n, so 2 to the n, 2 to the n, 2 to 1/2 to the 2n, which is 1. Okay, so hopefully this calculation is enough. Okay. So which proof that the norm of psi 1 is psi 2. Remember that I forget about this 1 divided by 2, right? So it's 1 divided, so if I square is 1 divided by 4, 2 plus 2 5. It's 1 plus 5, 2 fh. Okay, and basically you can see this is the same as Aronson's paper. Aronson's this is the same equation in Aronson's paper in 2014. This is basically this. Okay, so the probability that you measure plus is basically 1 plus phi of fh divided by 2. Okay, and there's an idea called promise problem. Basically, if you define your f phi to be small, very small, or very large, then your BQP algorithm can run this Forrelation and find. And but there's a lower bound on this problem that yeah, for the classical one, there's a I think there's a lower bound which can prove, which is much more difficult. And this Forrelation is powerful that it can provide the separation between the BQP and the pH. which is much more difficult. Okay, see you guys in next videos.